Okay, so let's talk about standard conditions. So the standard state is the state of a material that is defined as a set of conditions. Pure gas at exactly 1 atm of pressure, pure solid or liquid is in its most stable form at exactly 1 atm of pressure and a temperature of interest, usually 25 degrees Celsius. Substance in solution with a concentration of 1 molar. So the standard state, remember when we talked about the standard state of gases, so STP, standard temperature and pressure, was 1 atm, 273 Kelvin, which is freezing. Well, for a pure solid or liquid, it's 1 atm and usually 25 degrees Celsius, which is about room temperature. And this is usually with a concentration of 1 molar. So the standard enthalpy change, and that's delta H with the degree sign, is the enthalpy change in which all the reactants and products are in their standard states. Okay, makes sense. Standard enthalpy change, they're in their standard states. Standard enthalpy of formation, delta HF degree, is the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. So it's the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. So the elements must be in their standard states, and the heat of formation for a pure element in its standard state is 0 kilojoules per mole. Okay, so the heat of formation for a pure element in its standard state is 0 kilojoules per mole. So here are different standard enthalpies of formation. Think about this. So we've examined 2 ways to determine delta H for a chemical reaction: experimentally through calorimetry and through Hess's law. We now turn to a third and more convenient way to determine delta H for a large number of chemical reactions from the tabulated standard enthalpies of formation. So this is an easier way of finding basically delta H. So these are standard enthalpies of formation. So this is, look at what they're at. So it's the heat of formation at 298 Kelvin. So this is at room temperature. So here's bromine as a gas, bromine is a liquid, hydrobromic acid. Now these are not all of the standard heat of enthalpies. On the test, you will have all of them because you're going to need to use it. You're going to need to use the heat of formation in an equation that we're about to look at. Okay, so this. I'm going to skip this and go back to this. So, the standard enthalpy of formation is also called the standard heat of formation. Assigning the value of 0 to standard enthalpy of formation for an element in its standard state is equivalent of assigning an altitude of 0 at sea level. Once we assume that sea level is 0, we can then measure all subsequent changes in altitude relative to sea level. Similarly, we can measure all changes in enthalpy relative to those of pure elements in their standard states. For example, consider the standard enthalpy of formation of methane gas at 25 degrees Celsius. So standard enthalpy of formation of methane gas at 25 degrees Celsius would be this. So you have carbon. This is the same formula we've been using. Or no, this is a different one, sorry. Hydrogen. H2, 2H2 gas. And that yields CH4. And our heat of formation equals negative 74.6 kilojoules per mole degrees Celsius. Okay. So it says the carbon in this equation must be graphite, the most stable form of carbon at 1 atm and 25 degrees Celsius. This is pencil lead, basically. For methane, with the most compounds, the standard heat of formation is negative. So for methane, with most compounds, the standard heat of formation is negative. Continuing our analogy, if we think of pure elements in their standard states as being at sea level, then most compounds lie below sea level. The chemical equation for enthalpy of formation is of a compound is always written to form 1 mole of the compound. So delta H of formation has the units kilojoules per mole, and it lists delta. So that chart that was back here is going to list it in kilojoules per mole for the heat of formation. So let's talk about formation reaction. So reactions of element in their standard state to form 1 mole of a pure compound. If you are not sure what the standard state of an element is, then we can look at that chart and find it. Because the definition requires 1 mole of a compound to be made, the coefficients of the reactions may be fractions. So usually it's 1 mole of the compound to be made. Okay, so that means that some of the reactants may be a fraction. Okay, so the formation of a reaction is the reaction between the elements in the compound, which are carbon and oxygen. The elements must be in their standard state. There are several forms of solid carbon, but the one with the heat of formation equals 0 is graphite. Oxygen's standard state is the diatomic gas. The equation must be balanced, but the coefficient of the product must be 1. Okay, so use whatever coefficient in front of the reactants is necessary to make the atoms of both sides equal without changing the product coefficient. So since we have 2 oxygens here and 1 in the product, in order to balance it to where we still have 1 mole of the product, you have to put a 1/2 in front of the oxygen. So calculating standard enthalpy change for a reaction, any reaction can be written as the sum of formation of the reactions. Before we go on to this, let me look at that example. Yeah, so here's an example. It says, write equations for the formation of magnesium carbonate and glucose from their respective elements in their standard states. Include the heat of formation for each reaction. So we're going to write the equation of the elements of magnesium carbonate in their standard states as a reactant, and 1 mole of magnesium carbonate is the product. Balance the equation and look up the heat of formation in the appendix 2B. That's what I'm going to provide for you. It's a chart. Use fractional coefficient so that the product of a reaction is 1 mole. So we got magnesium, carbon, and oxygen. Well, in order to have still have 1 mole of magnesium carbonate over there, you have to put the coefficient of oxygen as 3/2, and that way it will stay at 3 oxygens on both sides. And the heat of formation, they got this from that chart. So in this chart, they actually tell you the heat of formation of magnesium carbonate. Here's glucose. We got carbon, hydrogen, oxygen, forms glucose. So in order for it to stay as 1 mole, well, this one's easy because you can just put whole numbers of coefficients to keep it that way. And again, we got this heat of formation from that appendix. Okay, so